Hi, in this screencast we're going to be analyzing the results of different neural networks with different numbers of hidden layers. So in the previous screencast I showed you how to set up code for fitting neural networks with different numbers of hidden layers. And in this screencast what we're going to do is analyze those results. So here after doing that whole computation, I have this layers metrics data table where we have different columns. So the first column is number of hidden layers. Then we have columns for validation loss and accuracy, train loss and accuracy, and then the number of epochs. So we trained each model with a different number of hidden layers for 100 epoch. And so what we want to figure out is what is the best number of hidden layers to use. So let's look at that with the geom line. Here we're going to be putting again the number of epochs on the x-axis, the validation loss. Why don't we actually train? Look at the validation and the train loss like we did before. So going back up, let's copy this block of code that we used for the hidden units, because that's essentially the same plot that we want to make here. So here, let's again do a find and replace of units for layers. And so let's look at that first. This layers metrics tall, this is going to be a reshaped version of that previous data table, where here we have the value column, which has both the loss and the accuracy for both the train and the validation set. If we take that and then just consider the loss and then just compute the min values and send it to this ggplot, so again we have to use library ggplot2 to get that attached. After that we can plot it. And so here's what we get. So this is kind of interesting, right? So in every case, we see that the subtrain loss is always going down here with some slight variations here when we start to have a large number of layers. Okay, so again, what we're plotting is, in every different panel, is the number of hidden layers. 0 hidden layers, that's a linear model. 1 hidden layer, that's what we've been doing before. 2, 3, 4, 5, these are different numbers of hidden layers with increasing model complexity, right? And so what we see is that we see the characteristic subtrain validation curves. Our subtrain is always going down. Validation loss is going down and then back up again in every case. And what we see is something pretty interesting, is that it looks like the min validation loss is going down and then back up again. So to see that more clearly, what I mean is that here it looks like the validation error is relatively high, then it goes down, and then it looks like it starts to go up again. So let's take a look at that in another plot. So here those dots that we were plotting are layers loss min at the geom point right there. So if we take a look at ggplot geom line AES, and here what we want to do is we want to put hidden layers and then value, and then color equals set, and data equals layers loss min. So here what we should be able to see is the regularizing effect of the number of layers, right? So what we get is that, again, here this is a plot of the number of hidden layers from 0 to 5 versus the validation and the train loss, right? So here the legend doesn't quite match up with the curves, so one way to get a better looking figure would be using my directlabels package, directlabel gg last polygons plus xlim 0, I don't know, let's go all the way up to 8 instead of 5. Probably didn't need to go that much, maybe just up to 6. Alright, so what we see is that the subtrain loss goes down as a function of the number of hidden layers, right? So if we want to, here on the y-axis it says value. If we wanted to make this clearer what we're actually plotting, we could actually add a facet, a grid. What is this column? It's metric, tilde. There's only one value of metric, but here, at least now we're drawing something that says loss to make it clear that here we're plotting the loss as a function of the number of hidden layers. Here for the subtrain set, it's always going down pretty much. And that's to be expected, right? So the more layers you have, the more model parameters you have, and so the easier it is to fit your training data. However, for the validation loss, we see, what is really typical, that is, it goes down and then it starts to go back up again, right? So at 0 hidden layers, that's not enough parameters to do good generalization. At 1 hidden layer, we're doing a pretty good job, and then starting after 2 hidden layers, we start to overfit, right? So what this plot suggests is that we should select 1 hidden layer for our neural network architecture. So thanks for listening to the screencast. Again, what we were trying to show, we were trying to analyze the regularization effect of the number of layers in the hidden the number of hidden layers in the neural network. And what we showed is that indeed it has a regularization effect, right? So we can see that the model complexity is increasing as we add the number of hidden layers, and after a certain number, here the maximum number is 1, the best number of hidden layers is 1, we start to overfit, right? The validation loss starts to go up. So this is not true for all data sets, right? So this is the spam data, and your mileage may vary. You apply this to another data set, you may have 2, 3, 4, 20, 30, 40 hidden layers, which is optimal. And there's some neural networks now that are like extremely deep with like hundreds of hidden layers. So it really depends on the complexity of your data. Here we only have about 1,000 observations in the train data and validation data set, so it makes sense. It's a relatively small, simple data set, so it makes sense that we only need 1 hidden layer. With larger data sets, we might need to have more hidden layers, and that's a good rule to keep in your head. Big data, more parameters, more layers, more hidden units. Okay, thanks for listening.